Okay, everyone. Few students, please put your video on. Yes. Few other students, please put your video on. So we'll be starting with reagents and mechanisms. We already understood the basic difference between electrophiles and nucleophiles and how to understand a given thing as an electrophile or a nucleophile, right? So I have listed out again few differences between electrophiles and nucleophiles. Let us quickly go through this and we will move on to the chapter. Electrophiles are electron loving species or the electron seeking reagents, or they are electron deficient species. As they are electron deficient, hence they are going to seek the electrons. Nucleophiles seek positive center, or they are electron rich species, or they are nucleus loving species. In general, electrophiles are positively charged reagents like H positive, carbocation. But all of the positively charged species may not be acting like electrophiles. Reason being, if their octet is already complete, if they cannot accept a pair of electrons, then in that case, they may not be acting like an electrophile. We have seen such examples as well, right? And nucleophiles, in general, they are negatively charged species like OH minus, carbanion, RO minus alkoxide, halide, carboxylate. Negatively charged species are nucleophiles. They can be neutral reagents as well, electrophiles. Free radical BF3 is electron deficient species because its octet is incomplete. Hence, BF3 can act as electrophile. Carbene is also electron deficient species. It also has 6 electrons in its valence shell, carbene. So it's also an electrophile. AlCl3 is also an electrophile. All these are Lewis acids because they can accept AlCl3 is a Lewis acid, BF3 is a Lewis acid because they can accept a pair of electrons. Even Br2 can act as electrophile because it has vacant orbitals. Okay, bromine has vacant orbitals. So into those vacant orbitals, the electrons can be donated. Once some electrons are getting donated into the vacant orbitals of bromine, then Br2 will break as some Br positive and Br negative. Okay. But the reason for this acting like an electrophile is due to the availability of vacant orbitals inside the bromine. Then the neutral reagents can also act as nucleophiles whenever you have a lone pair of electrons, like NH3, RNH2, H2O, alcohol. Whenever you have lone pair of electrons, all these can act as Lewis bases or they can act as nucleophiles. All Lewis acids are can be termed as electrophiles. Similarly, Lewis bases can be termed as nucleophiles. Metal ions with vacant d orbitals like Fe3 positive, Hg2 positive. Whenever you have vacant orbitals, into those vacant orbitals, you can give the electrons, hence it can act as electrophile. Organometallic compounds like the Grignard reagent, we understood this in alkanes chapter. This is an organometallic compound where you are having a bond between carbon and the metal. Carbon being more electronegative, it will be having significant amount of negative charge. And for all problem solving purposes, we will be taking that as R minus and Mg positive. We treat this as an ionic bond, but this is not an ionic bond. It is covalent only. It is predominantly covalent. Hence, we write it as R minus Mg positive X. Once it is a source of R minus, it can act as nucleophile. Right? Okay. Yes. Then I have written one point here. Very important. In general, there is no difference between electrophilic and Lewis acidic strength. Electrophilic strength and Lewis acidic strength. What do I mean by that? If you try to do the comparison of Lewis acidic strength of different compounds, what is meant by Lewis acid? One is one which accepts the lone pair of electrons. So the one which has the highest tendency to accept the lone pair of electrons will be a stronger Lewis acid, right? That will also become the stronger electrophile as well. So in general, whenever you mark the comparison of Lewis acidic strength and electrophilic strength, there won't be any difference. But whenever you mark the comparison of nucleophilic strength and basic strength, okay, every nucleophile can act like a base and every base can act like a nucleophile. What's the difference? We will understand the difference. Whenever it is acting like a base, why am I calling it separately as a base and why am I calling it as separately as a nucleophile? The same compound can act as nucleophile as well as base. We will understand what is the difference between a base and nucleophile in some time. But whenever you mark any compound or any set of compounds basic strength and nucleophilic strength, the order may not be the same. The order of nucleophilic strength and the order of basic strength may differ. Again, we will understand in this lecture, we will be understanding why there can be difference between a basic strength order and nucleophilic strength order. Okay. So let us understand what happens when some reagent acts like a nucleophile and once some reagent acts like a base. Yes. So basically bases capture protons while nucleophiles attack an electron deficient atom such as a carbon. What do I mean by this? Suppose let us say you have this carbocation, the carbon attached to any functional part or any part that is responsible for some reaction is known as alpha carbon, right? So this carbon is the alpha carbon and the hydrogen that is present on that is the alpha hydrogen, right? Okay. So whenever you have a negatively, as for example, I'm taking a negatively charged species, but you can also have a neutral species acting like a nucleophile or a base. Suppose you have this negatively charged species. If this negatively charged species is attacking on this particular electron deficient carbon, okay, in that case, we call this negatively charged species as a nucleophile. It is going and donating its electron pair into the vacant orbital of this carbon. Initially, the carbon is sp2 hybridized. So whatever pure p orbital is there, this negative charge is getting donated inside that pure p orbital. Can I say that? Okay. Once it forms the bond, the hybridization of the carbon changes into sp3. Initially, it's pure p orbital, but during the process, during the formation of the bond, there will be transition of the carbon's hybridization from sp2 to sp3. Everyone. Okay. So whenever this negatively charged species is going and attacking an electron deficient atom, in that case, we will call this negatively charged species as a nucleophile. But if the same negatively charged species, if it attacks the alpha hydrogen, if it attacks the alpha hydrogen, in the process, what will this negatively charged species does? It will be attacking it. Whenever it is attacking it, this will be removed as H positive, and this Y negative will be accepting the H positive. In the ionic equilibrium, we have seen that one which accepts H positive is a base and which donates the H positive is an acid, right? What is that theory? Bronsted acid base theory?
Yes, sir.
Yes, one which accepts H positive is base, one which gives H positive or donates H positive is an acid. So when this negatively charged species, rather than attacking at this particular electron deficient carbon, if it is attacking at this particular hydrogen, then we say it's a base because it's accepting a H positive. So the same negatively charged species can have two behaviors, one as a nucleophile, one as a base. And why am I saying that the nucleophilic strength may not be equal to the basic strength? The reason for that is because of the nature of the attack. Whenever the negatively charged species is attacking at this particular carbon, it has to satisfy several conditions. That is, it has to first orient its electrons towards this particular carbon, that is, towards the vacant orbital of the carbon, right? You have a p orbital. Whenever these electrons are oriented towards that particular p orbital, then only there can be overlap. Whenever there is effective overlap, then only there can be bond formation. Agreed?
Yes.
Okay. So there is some orientation problem happening in this particular attack. There will be some energy barrier, there will be some orientation barrier. So this particular property depends on the kinetics of the reaction. In the chemical kinetics, if you remember, we understood about the orientation barrier, the probability factor, okay, as well as the energy factor. And based on all these things, you will be having dependence of the rate constant. Agreed? Okay. But whenever the same negatively charged species, if it wants to attack on this hydrogen, we know that hydrogen has s orbital, and s orbital is spherically symmetric. And s orbital being spherically symmetric, it does not have any orientation barrier. Agreed? Moreover, it need not go and collide with it as well. Reason being, initially there will be some partial negative, partial positive charge on the hydrogen. Whenever it approaches near the hydrogen, there will be starting of the ionic interaction. Because of the ionic interaction happening, the hydrogen and carbon bond may break, and eventually the bond between hydrogen and this negatively charged species is going to form. Okay. So this aspect, this particular reaction depends on every acid base reaction is studied with respect to thermodynamics. Okay, it is not a kinetic problem, it is a problem of thermodynamics, everyone. In thermodynamics, if you remember, we have studied about heat of ionization as well as heat of neutralization. Remember, whenever you have a strong acid, strong base titration, or whenever you mix a strong acid with a strong base, the amount of heat released when one equivalent of an acid combines with one equivalent of base is how much? 57.3.
Enthalpy of neutralization.
Yes, enthalpy of neutralization, which whose value is around 57.3 kilocalories, right? If I'm not wrong.
I think it's
Joules.
Joules.
3
Okay,
kilojoules,
okay.
sir.
Yes, yes, kilojoules. Yes, that's right. Okay. So whenever you have a weak acid reacting with a strong base, in that case, the amount of energy that is going to be released will be lesser. And whichever amount that got decreased, that is known as the heat of ionization of the weak acid or weak base, right? So the acid base reaction is a thermodynamic property. It is not at all related to the kinetics of it. Okay, because we don't have any orientation barrier. The only barrier which you have is breaking of that particular acid in order to furnish H positive. Is this clear, everyone? Okay.
yes, sir. Sir, I have a doubt.
Yes.
So here, basic strength is moved as a Bronsted-Lowry base or as a Lewis base, right?
Yes. Basic strength can be treated as a Lewis base or a Bronsted-Lowry base as well.
Yes. And both can differ with nucleophilic behavior, right?
Yes. Both can differ with nucleophilic behavior, and in general, we in organic chemistry we talk about only Bronsted basic strength. Okay, whenever they are asking about the basic strength, we are it is implied that they are asking about the Bronsted basic strength. Okay.
Yes.
Sir,
Yeah.
sir, but a loose base is by definition a nucleophilic group, right, sir? So
Yeah. It can act as a nucleophile. A Lewis base can act as a nucleophile.
okay,
But
sir.
if the same Lewis base is accepting H positive, we will call that as a Bronsted base. That's it.
Okay.
Okay. A nucleophile, for our discussion, a nucleophile is one which is going to donate its lone pair of electrons into some vacant orbital. Okay. A base is one which is going to accept H positive. So whenever it is accepting H positive, it is not donating anything into the vacant orbital. It is trying to pull that H positive from a distance. Okay, once it is pulling that H positive, then the overlap will happen. Such things may happen, but you need not specifically target that particular negatively charged species towards that particular hydrogen in one specific orientation. It can approach from this side, this side, this side, any side is fine, as long as it is able to have some interaction with this positive, some delta positive hydrogen. You will understand. You will have more and more clarity. This is just the introduction. Just understand, when a negatively charged species is acting like a nucleophile, it is having some way of attacking. Whenever it is acting like a base, it has a different way of a different mechanism of attacking the hydrogen. Okay. And this basic behavior, basic strength is a thermodynamic property, and the nucleophilic behavior is a kinetic property because it is related to energy barrier, orientation barrier, such things. In here, it is only related to the amount of H positive that is available. So we will write two statements here. Basicity is a measure of how readily an atom donates its electron pair to a proton. It is characterized by equilibrium constant Kb and is therefore a thermodynamic property. All acid-base reactions are equilibrium reactions, everyone. Whenever you are having a weak acid, weak base reaction, you are having those reactions as an equilibrium reactions because on the left, if you have a strong acid, on the right, you will be having a conjugate base. And on the left, if you have a base, on the right, you have a conjugate acid. So whatever acid and base that are there on the left, they can react among themselves to form the compounds or the products on the right hand side, which are again acid and base, which can again react among themselves, and we can have formation of the reactants. So all organic acids or organic bases are weak acid bases. So all of them are reversible reactions. So they are basically characterized by the equilibrium constant. Okay, and it's a thermodynamic property. But nucleophilicity is a measure of how readily an atom donates its electron pair to other electron deficient atom. It is characterized by the rate constant K, making it a kinetic property. Everyone with me?
Yes.
Okay. So we understood that whenever a negatively charged species acts as a base and a nucleophile, its behavior is quite different. So their orders, the strength of or the nucleophilic strength order and the basic strength order may or may not be same. But there are some cases where the nucleophilic strength parallels the basic strength. That is, the basic strength order and the nucleophilic strength order will be exactly the same. So let us understand the cases where they are the same. Okay, for other things, we will be comparing based on the question. So nucleophilicity parallels basicity in 3 instances. That is, the first case, for 2 nucleophiles with the same nucleophilic atom, the stronger base is the stronger nucleophile. That is, if you compare the basic strength order, the basic strength order will be equal to the nucleophilic strength order. Suppose let us take these two bases. You are taking alkoxide and carboxylate. We know that carboxylic acid is a stronger acid when compared to alcohol, right? So the acid being a stronger acid, carboxylic acid being a stronger acid, its conjugate base will be a weaker base when compared to alkoxide. So alkoxide is a stronger base. So if I compare the basic strength order, CH3O minus is greater than CH3CO minus, and that will also become the nucleophilic strength order. Okay. If you ask me which is a stronger nucleophile among these two, alkoxide is a stronger nucleophile when compared to carboxylate. Everyone clear? And this must be compared, everyone, this must be compared if and only if you are comparing the nucleophilic strength of two different functional groups. What do I mean by this? In this case, you have a carboxylate which is formed from a carboxylic acid, which is a different functional group. You are comparing alkoxide with a carboxylate, and alkoxide is the one which is formed from alcohol functional group. Suppose if you are comparing among the same functional groups, that is, let us take this. You have alkoxide. This is also an alkoxide. This is also an alkoxide. Okay. If you want to compare the acidic strength order, suppose let us directly compare the basic strength order. Everyone, this is a stronger base, right? Because you are having a electron releasing group, and this is a larger carbon chain. So this is a stronger electron releasing group or a greater plus I group. We know that electron releasing groups increases basic strength, and withdrawing groups decreases basic strength. Everyone, is that right?
Yes.
Yes, sir.
So you have a negative charge, you are further pumping in some amount of negative charge. So the electron density is getting increased, you may say that, and this will immediately combine with the H positive, making it a stronger base. Okay. So in this case, if we apply the same logic for two nucleophiles with the same nucleophilic atom, if you observe, this is also a oxygen, this is also oxygen, both of them are same nucleophilic atoms. So if you say that this will be a stronger nucleophile when compared to this, it may not be appropriate. Why is it not appropriate? If you observe, this has become a bulkier base when compared to this. Agreed?
Yes.
Whenever this has become a bulkier base, if it has to act as a nucleophile, during nucleophilic behavior, what is happening? The negatively charged species has to orient itself along the direction of the p orbitals, and then it has to attack on that particular carbon. Agreed?
Yes.
So you will be having some amount of steric hindrance because of its bulky nature. As a result, the nucleophilic behavior or the nucleophilic strength will be decreased. So in this case, you have exactly the reverse order of nucleophilic strength. That is, this is a better nucleophile when compared to this because of its smaller size. So this particular point, whatever I have written here, for two nucleophiles with same nucleophilic atom, stronger base is the stronger nucleophiles is in general applied to different functional parts. Okay. Once they belong to different functional parts, you don't worry about the size of this. So these are of comparable size. Suppose if I give you something like CS3, CS3 or CS3, CS2, 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 CO minus, in that case, it has become so bulky. Again, you may have to take into consideration of steric hindrance. Okay. So that you can analyze question to question basis. As of now, let us consider or these two are of comparable size. You need not worry about the size factor here. In this case, because of the delocalization of the charge, you are having very less amount of charge present on each of the oxygen atom. As a result, it has become a poor nucleophile, poor base as well as poor nucleophile. In this case, even though this is a stronger base because of the predominant electron releasing group, if you look at the nucleophilic strength, this is a better nucleophile when compared to this because of the bulkiness. Everyone with me?
Sir, more the spherical nature of the atom.
You need not go into the spherical nature and all. It's not necessary. It's just bulky. You can see this as bulky, right? It has only 2 carbons. This has 3 carbons. So the size got increased. The bulkiness got increased. Okay.
Understood, sir.
And during basic strength comparison, you need not worry about this bulkiness. What is the reason for that? Because it can go and attack from any direction. Moreover, it need not exactly go and overlap with this hydrogen. It has to just generate some ionic interaction between the negative charge and partial positive charge, and the hydrogen can be pulled from a distance. Okay. So the problem of bulkiness in general, again, this is in general, may not be a factor during the attack on the proton. Okay. When it is going to matter, we will understand later. As of now, the problem of bulkiness may not be a factor for the basic strength comparison. Hence, this becomes a stronger base when compared to this. You just need to compare the basic strength order, which we usually compare using the GOC principles. Everyone with me?
Yes, sir.
Yes.
No. Next, a negatively charged nucleophile. This will hold true for everywhere. A negatively charged nucleophile is always a stronger nucleophile than the conjugate acid. That is a neutral nucleophile. CS3O minus is always stronger base when compared to CS3OH. Similarly, CS3O minus is always a stronger nucleophile when compared to CS3OH. Acetate is always a stronger base when compared to acetic acid. That is, if I'm looking at the lone pair of the oxygen. Okay. In general, acetic acid's basic strength we won't be comparing because in general it is not at all a base. But I'm just saying this negatively charged is always a stronger base when compared to this neutral base. So this will always be a stronger nucleophile when compared to this neutral nucleophile. OH minus is always stronger base when compared to H2O, as well as it is a stronger nucleophile when compared to H2O. Everyone with me?
Yes,
Yes.
sir.
I'll share the notes towards the end of the lecture. Don't worry. Just focus on understanding part. Next, comparison in a period as well as in a group. Okay. If we look at the basic strength order, I hope every one of you can compare the basic strength order quite easily based on your GOC understanding. CS3 minus NH2 minus OH minus F minus. Okay. This carbon is having, whenever you are comparing anything in a period, the dominating factor becomes electronegativity. So carbon being less electronegative, it cannot effectively handle the negative charge. Hence, it's always a stronger base when compared to F minus, which is able to effectively handle the negative charge. So the basic strength order is CS3 minus greater than NH2 minus, OH minus, and F minus. Or you can compare the acidic strength order in order to get the basic strength order. Either way is fine. That is exactly equal to the nucleophilic strength order. Whatever basic strength order you have, that will be equal to the nucleophilic strength order. This is with respect to period. But whenever you take a group, okay, this is the order of basic strength, right? F minus, Cl minus, Br minus, I minus. Because in a group, what is the dominating factor? Size is the dominating factor. So I minus is able to handle that negative charge well because of its lesser charge density. Okay. That same negative charge is spread in a larger volume Hence, we can say it is like a distributed density. Once it is a distributed density, you will be having a lesser basic strength. F minus, the negative charge is concentrated in very small region, hence it is highly unstable, or it is the density being higher, it is available for the incoming H positive. So F minus is stronger base, Cl minus, Br minus, I minus. Okay. So what can you comment on the nucleophilic strength order? What do you feel?
Sir, the same as the basic strength.
Same as the basic strength. Okay. So in this case, the role of solvent also matters in comparison of basic strength, everyone. The role of solvent doesn't matter in comparison of basic strength for the elements belonging to same period. It doesn't matter because all of them will be equally solvated. The size difference among CS3 minus, NH2 minus, OH minus, F minus is not so huge. But in a group, the size difference among the ions is very huge, everyone. So the solvation effects are seen greater for the elements belonging to same group when compared to the elements belonging to the same period. So we need to also consider the effect of solvation. How exactly the solvation will determine the nucleophilic strength? Let us understand that. Suppose if you have H2O, which is a polar protic solvent, right? Everyone, do you have the understanding of polar protic and polar aprotic solvents? Did we ever discuss among them differences between them?
I don't think so. We covered protic and
I don't
aprotic.
think so, sir.
Protic and aprotic we didn't, right? Okay. So let's go into that particular aspect first. Everyone, basically we have, if you classify the solvents, what are the types of solvents you have?
Polar, non-polar.
Polar, non-polar. We have non-polar as well as polar solvents. Non-polar solvents are those where mu equals to 0. Polar solvents are those where mu not equals to 0. And as we are talking about ions, ions are usually soluble in polar solvents, right? So our point of interest is the polar solvent, or ions usually exist in polar solvents. Hence, we need to consider polar solvents. I'm not discussing about any non-polar solvent. And among polar, non-polar, among polar solvents also, we have two different solvents. One is called as polar aprotic solvent, and the other is called as a protic solvent. Aprotic solvent is one which cannot furnish H positive. Cannot furnish H positive. Protic solvent is one which can furnish H positive. Okay. What are the solvents which cannot furnish H positive? Whenever the hydrogen is attached to highly electronegative elements like oxygen, fluorine, nitrogen, in all those cases, H positive can be furnished. Okay, in those cases, we will be calling it as a polar protic solvent. If the hydrogen is not attached to any of these, suppose if you have acetone, CS3, C double bond O CS3. In this case, the hydrogen is not attached to oxygen, it is attached to carbon, right? So the H positive may not be furnished easily, or this is a very weak acid. In its solution, you won't be having a significant dissociation of acetone into CS3, C double bond O CH2 minus and H positive. Okay. So you will have very less concentration of H positive in the equilibrium, or it can be treated as an aprotic solvent. Okay. Then you have DMF, dimethyl formamide. This is known as formamide, an amide which is made from formic acid. HCOH is formic acid. An amide is a derivative of carboxylic acid. Okay, if you replace the OH with NH2, it is called as an amide. So this is called as formamide, dimethyl formamide. Dimethyl. or N, N dimethyl formamide. This is known as DMF. DMF, which is a again standard polar aprotic solvent. It's a polar solvent. I hope every one of you will agree it's a polar solvent. And it is an aprotic solvent because the hydrogen is not connected to either nitrogen or oxygen or fluorine. Okay, hence it is an aprotic solvent. And it is polar, hence it is polar aprotic solvent. Then we also have something called DMSO, dimethyl sulfoxide. Okay, so if you have this is known as dimethyl sulfoxide. Okay, DMSO. This is also polar aprotic solvent. Then what are polar aprotic solvents? Which are able to furnish H positive, H2O, HF, okay, amines, RNH2, acetic acid, CS3COH. All these are protic solvents because they can furnish H positive. Everyone with me? Okay. Okay. Them being polar, okay, them being polar, I can always represent either of both of them as some dipoles, right? Polar protic also as a dipole, polar aprotic also as a dipole. But the difference between an aprotic dipole and a protic dipole is, in case of, let us take some example. In case of an aprotic solvent, if I take acetone, you have some negative charge here, some positive charge here. But the amount of positive charge is often decreased by some electron releasing groups. Okay. If the amount of positive charge is decreased by electron releasing group, what happens is in the dipole, you have significant negative end, but the positive end is not so significant. Everyone understand this? A polar aprotic solvent, whatever dipole you have, the negative end is going to be significant when compared to the positive end. In all of the compounds, the positive end's charge is going to be decreased by some or the other factor, that is by some electron releasing group. Because of the electron releasing group, the partial positive charge gets decreased. Okay, in case of DMF, you have this lone pair participating in resonance. Okay, so the amount of partial positive charge decreases. This partial negative, partial positive. Here also you have electron releasing group. Hence, again the partial positive charge decreases. Okay. So because of that significantly less amount of partial positive charge in the dipole, whenever you dissolve any ion or an ionic compound has some positive and negative species. So the positive part can be solvated, effectively solvated by the negative ends of the dipole. Everyone, whenever you have polar, let us take you are having polar protic solvent. In polar protic solvent, you will have in the dipole significant negative and significant positive end. As a result, both the cation as well as anion will be solvated effectively. Because of the strength of the dipole or because of the significant positive end as well as negative end, this negatively charged ion will be solvated by positive ends of the dipole, and you have a significant positive end in case of a polar protic solvent. Everyone, if you have a polar protic solvent, the polar protic solvent is going to effectively solvate the anion as well as the cation. But if you have a polar aprotic solvent, polar aprotic solvents significantly solvate only the cation part. The anions are not significantly solvated because of the weaker positive end inside the dipole. Everyone with me?
Yeah.
Okay. If that is the case, what happens is, everyone, we are comparing the basic strength for the elements belonging to the same group in two different solvents, in H2O as well as DMF. In H2O, H2O being a polar protic solvent, okay, H2O being a polar protic solvent, it can effectively solvate the positive cation as well as the negative anion. We are interested in the negatively charged species because negatively charged species are those which are acting like either a base or a nucleophile. Agreed? Okay. So all these F minus, Cl minus, Br minus, I minus are going to be solvated inside water. And what is the order of solvation? Greater is the charge density, more is the solvation. F minus being highly unstable. F minus being highly unstable, it is going to be solvated to the highest extent. Once it is solvated, what will happen to the size of that particular F minus? It increases. Everyone,
Yes.
Yes,
F
sir.
minus is getting solvated, it is becoming bulkier and bulkier. Once it becomes bulkier, what will happen to its strength as a nucleophile? Whenever I'm talking about nucleophile, you need to visualize it as less bulky as possible because it has to go and donate its electron pair in some orbital. So there will be some orientation problem. So if you are having a bulkier molecule, its reactivity as a nucleophile is going to be decreased. So once F minus is solvated to the highest extent in the polar protic solvent, it becomes the weakest nucleophile in the polar protic solvent. So the order of nucleophilic strength becomes I minus greater than Br minus F Cl minus F minus. If you compare the conjugate basic strength, I minus is the weakest base. Everyone, I minus is the weakest base, but with respect to the nucleophilic strength in polar protic solvent, it has become the strongest nucleophile. But if you compare the same nucleophilic strength order in DMF, which is a polar aprotic solvent. In polar aprotic solvent, there is no question of solvation of the negatively charged species. Whenever it is not solvated, you compare as per the basic strength order. Stronger base will be the stronger nucleophile. F minus is the stronger base because HF is the weakest acid. So F minus will become the stronger nucleophile. Is that clear?
Sir,
Yes.
sir, between solvation and nucleophility, more solvation means the lone pair isn't available. Like, could you update that?
You can understand it like more solvation means it has become more bulky. So let us take this as the anion. If it is becoming more and more solvated, it has become more bulky. So it cannot go and attack. Okay. It has to attack on this negative charge must be donated into some orbital, right? Some vacant orbital. So the attack becomes difficult because of the solvation.
Okay, sir.
Okay, just understand it has a nucleophile. Whenever it becomes bulky, it becomes a poor nucleophile. Okay.
Yes.
In F, so here also you can say in DMF, F minus, Cl minus, Br minus, I minus. F minus, I am considering it as a better nucleophile because if you compare the basic strength order, this is the basic strength order that will become the nucleophilic strength order. You can also compare that based on the size. I minus is a larger one when compared to F minus. Hence, I minus has become a poor nucleophile. But after solvation, if you see, I minus has become the largest, F minus has become the largest nucleophile. Hence, its nucleophilic strength got decreased. You need to look into solvation effects. Solvation effects happen often only if it's a polar protic solvent. A polar protic solvent solvates both the cation and anion effectively. A polar aprotic solvent is not able to solvate a negatively charged species or a nucleophile effectively. What's the reason for that? Because in the dipole, the positive end is not so significant. The positive end in general is not so significant because of the electron releasing groups present in the polar aprotic solvent. Everyone with me?
Yes, sir.
Okay. So the magnitude of solvation or hydration, it is directly proportional to charge density, right? So the order of hydration is F minus is highest, followed by Cl minus, Br minus, I minus. If this is the order of hydration, the order of nucleophilicity will be exactly reverse. Nucleophilicity depends on approachability and ionic mobility. Okay. So nucleophilicity order will become I minus greater than Br minus, Cl minus, F minus. In case of polar aprotic solvents, anions cannot be effectively solvated in polar aprotic solvents. Hence, the ionic radius order is F minus less than Cl minus, Br minus, I minus. If this is the order of ionic radius, the order of nucleophilic strength will be F minus greater than Cl minus, Br minus, I minus. Okay. So nucleophilicity is going to parallel Okay, basicity order, that is the order of basic strength and nucleophilic strength order will be exactly same. If at all you are comparing the ions belonging to same period. Once again, I am repeating this. In the period, the solvation effects won't be that great because already the difference in sizes of these ions is not so high. Whenever they are solvated, polar aprotic or protic, they will be solvated to the similar extent. So you need not compare based on the size. Solvation has greater effect for the elements belonging to the same group because the order of solvation is going to be clearly different because their sizes and charge densities are clearly different. Everyone with me?
Yes, sir.
Okay. So once again, anesthetically hindered bases are always poor nucleophiles. CS3O minus and this, if I want to compare between these two, this is a stronger base because you are having greater electron releasing groups. But if you compare the nucleophilic strength, this is a better nucleophile because of the smaller size of it. Okay. So what's the conclusion of this? First of all, the important take-home message is you need to understand the basic difference between a base and a nucleophile. The same species can act as a nucleophile as well as a base. Okay, whenever something acts like a nucleophile, it will be going and forming bond here, everyone. It is going to form bond here. In that case, what reaction is happening is you will be having a substitution reaction. If you have the same negatively charged species abstracting a proton from the alpha carbon, you will be having an elimination reaction. So the same negatively charged species, whenever it does an elimination reaction, you will be forming an alkene. If it does a substitution reaction, you will be forming an alkyl halide. So you need to know the comparison of or when a particular species is having favorable condition in order to act like a nucleophile. When it is having a favorable condition in order to act like a base. You need to know this. Then only we will be forming an alkene or you will be forming an alkyl halide. Hence, we are not directly jumping into elimination reactions. I hope you are able to connect why we are doing this. Everyone.
Yes, sir.
Yes, sir.
Yes.
Yes. Then you need to understand what are the cases where nucleophilic strength order parallels basic strength order. I have written a few cases where nucleophilic strength order and basic strength are the same. And whenever there is a difference also, we understood why there is difference. Shall we go ahead?
Yes.
I'll share the notes. You go through the notes. We will again have discussion tomorrow. Don't worry. This is the order of nucleophilic strength among these four bases. CS3O minus greater than, ethoxide greater than, okay, isopropoxide greater than. Okay, this is tertiary butyl, right?
Yes.
Fine. Okay, next. So let us start our understanding with substitution. Everyone, we are taking a detour. We are first doing substitution, then we will be going to elimination, then we will be understanding the preparation of alkenes based on elimination reactions. Okay. Okay. So we will be understanding substitution reaction using the substrate alkyl halide. Alkyl halides are very good substrates for both substitution as well as elimination. Hence, we are taking alkyl halides to understand this. That doesn't mean you will have substitution and elimination only in case of alkyl halides. Or alkyl halides, the characteristic reactions of alkyl halides are both substitution as well as elimination. Okay. Once again, whatever we did, a quick recap. If a negatively charged species goes and attack on an electron deficient atom, then we will be having a nucleophilic reaction or you will be having a substitution reaction. If you observe here, in the initial example, I have taken carbocation. If you observe in this, in order to explain here, I have taken a carbocation. But in here, I am not taking any carbocation. I am simply taking some alkyl halide and I am showing some partial positive and partial negative charge. Because of the presence of the partial positive charge, this has become electron deficient. Hence, the nucleophile is approaching this carbon. But without breaking this carbon halogen bond, I cannot form any bond with the nucleophile because carbon's valency is only 4. It cannot expand its octet. Okay. So whenever this nucleophile approaches this carbon, this bond has to break. Okay. So whenever the bond is breaking, you can have two different types of reactions. That is, before approach of this nucleophile only, this carbon halogen bond got completely polarized, or it got broken completely, leading to the formation of carbocation and X minus. Then the nucleophile can come and attack, forming some bond. That is one way of mechanism. The other way of mechanism is whenever the nucleophile is approaching, whenever it is forming a bond, during that process, the carbon halogen bond is going to break, which is different from the initial mechanism, right? Initially, what did I say? The carbon halogen bond completely breaks. You will be forming a carbocation. Then the nucleophile is going to form the bond. What is the other type of mechanism? The carbon halogen bond is going to break during the formation of the bond between nucleophile and the carbon. It's another type of mechanism. Okay. Again, we need to understand when both the mechanisms are going to be favored. When will the carbon halogen bond can break immediately, forming a carbocation, then the nucleophile can come and attack. The other variation is when will that not break, the carbon halogen bond will not break. It will break only when nucleophile is going to approach the carbon. These are the two variations. In both the cases, the end product is the same, which is substitution of the halogen by the nucleophilic group. But what difference can happen? If you have a carbocation, there can be carbocation rearrangement, right? A carbocation that is formed, if it is not stable, if more stable carbocations can be formed, there can be rearrangement of the carbocation, and eventually you can form a more stable or a compound which is formed from the more stable carbocation. But if you are not forming a carbocation, then there cannot be any rearrangement. It has to go and attack on the carbon on which halogen was initially present. Everyone with me?
Yes.
Okay, we will explore. We will explore all these things. Okay, but in either of the cases, we will be calling it as a substitution reaction. I'm calling it as substitution because this group is getting substituted by a new group. Okay, so whatever group I am removing, that is called as a leaving group, because this is the group that is leaving this particular substrate and it is giving way to a new group, incoming group. Okay, the incoming group is called as nucleophile and the outgoing group is called as a leaving group. We already studied something which is called as weaker is the base, better is the leaving group. Everyone, weaker the base, better is the leaving group. That is, it can easily leave the particular substrate provided it is a weak base. If it is a strong base, it will always have the tendency to attack back, or it will have greater interaction between the carbon and halogen. As a result, it is difficult to remove it. Hence, it becomes a poor leaving group. Okay. And so the thing you need to be aware of is weaker is the base, better is the leaving group. This is the statement. Weaker the base, better is the leaving group. Okay. So in general, if I want to do a substitution reaction, the reagent that is going to be used is called as aqueous KOH. Everyone, if you have aqueous KOH, you will be having a substitution reaction. Aqueous KOH, what it is going to furnish is it is going to furnish K positive and OH minus. OH minus is negatively charged. Rather than using only H2O, if you have H2O, H2O can also act as nucleophile. Okay. If you simply have H2O, which can be termed as hydrolysis of alkyl halide, which is hydrolysis of alkyl halide. If you have simply H2O, you can have, we have seen something like this in case of that Woods reaction. In Woods reaction, someone has mentioned that it should not be moist, it has to be dry because in the presence of water, there can be hydrolysis of alkyl halide. What do I mean by hydrolysis of
Instead of
alkyl halide?
forming R bond I, it forms R bond H.
Yes, R bond OH. The water with lone pair can also act as nucleophile. it can also go and attack on this carbon, making this X to leave. Okay, and you will be forming an alcohol. But always a water is a weaker nucleophile when compared to OH minus. In order to speed up the reaction or in order to have only that reaction, if you take OH minus is negatively charged. A stronger base is a stronger nucleophile. OH minus is stronger base when compared to H2O. Or negatively charged nucleophiles are always stronger than neutral nucleophiles. So in order to have a faster reaction, because this being a kinetic property, if I have OH minus, it will be a stronger nucleophile or you can have better attack, faster attack. Yes, Manideep, you are having some doubt? Manideep, you raised your hand.
Yes, sir. Could you explain why a stronger nucleophile attacks again?
A stronger nucleophile, see, it's like this. If you have negatively charged species, it is more unstable when compared to neutral. Agreed? Okay.
Yes, sir.
So that being more unstable, if it sees a slight amount of partial positive charge, it is sufficient for a stronger nucleophile to go and attack.
Understood.
But if you have a neutral nucleophile, as it is relatively stable, unless and until there is significant amount of partial positive charge, it is not tending to approach this particular carbon. There is no driving force, significant driving force for this nucleophile. It can act as nucleophile, agreed. But similarly, it should also look for a strong electrophilic center. Unless and until you have a strong electrophilic center, this may not have tendency to approach it. If it is negatively charged, it will readily go and approach. Fine, everyone? Okay, this is what happens during a substitution reaction. During elimination reaction, what happens? The same negatively charged species will be acting like a base, right? Just understand what's happening. You are having a leaving group. The base is going to attack the hydrogen which is present on the alpha carbon. Everyone. Okay. The base is going to attack on the hydrogen which is present on the alpha carbon. Sorry, which is present on the, my bad. This should be called as beta carbon. The carbon that is attached to the functional group is the alpha carbon. This is alpha, this is beta. Everyone. I have been saying this as alpha, this is alpha and this is beta. The carbon that is directly attached to the functional group will be called as alpha carbon. This is called as beta carbon. As the elimination is happening from the beta carbon or the beta hydrogen is getting removed, the elimination is also termed as beta elimination. Everyone. The elimination is also termed as beta elimination. This is alpha, this is beta. The hydrogen of the beta carbon is removed, hence it is called as beta elimination. I hope everyone is with me.
Sir, because the functional group itself is X here and not C or something.
Yes, functional group is, yes, exactly. Functional group is X here. So the carbon attached to this X is the alpha carbon. This is beta carbon. Yes.
Okay, sir, thank you.
Yeah. And in general, the reagent that is used for elimination is alcoholic KOH. See the difference. If you have aqueous KOH, it prefers to have a substitution reaction. And due to that substitution reaction, you will be having a substituted product. If you have alcoholic KOH, it prefers to have an elimination reaction. And the product of the elimination reaction is alkene. What's the reason for this? Why alcoholic KOH is preferring to have elimination reaction? Why aqueous KOH is preferring to have a substitution reaction? Let us understand that. What is meant by alcoholic KOH? Nothing but addition of alcohol or addition of KOH to alcohol. Addition of KOH to alcohol. Let us see the reaction. OH minus plus alcohol. What can happen? This can act like a base and this can act like an acid. If you have a proton transfer, you have C2H5O minus and H2O. We also know that a H2O is a stronger acid when compared to alcohol. Agreed?
Yes,
So this being stronger acid, in general, the reaction will be driven in backward direction. Okay. If you have backward reaction dominant, you have OH minus as the one which is acting like a base. Suppose in this reaction, I need to have elimination, right? OH minus is the one which is acting like a base. If you have predominantly forward reaction, you will be having C2H5O minus acting like a base. If you take OH minus, if you observe, this is a less bulky group. Agreed? So in general, OH minus is a better nucleophile than a base, or its nucleophilic behavior is greater than when compared to the basic behavior. Or it will always tend to do a substitution reaction rather than an elimination reaction. If you take C2H5O minus, this being bulky, relatively bulky, it will have greater tendency to abstract the beta hydrogen rather than going and attacking on this carbon. We have some other conditions as well. In order to make elimination more dominant when compared to substitution, we will explore them later. As of now, just understand that OH minus is a better nucleophile than a base. So if you have only OH minus, rest all other conditions, if I'm not talking about temperature, other conditions, because those conditions can also affect elimination as well as substitution. We will explore them later. Just understand now, OH minus being a smaller ion, it can have substitution significantly apart from elimination, or substitution is going to be dominant when you have OH minus. But if you have C2H5O minus, this has become bit bulkier. As a result, it will have a greater elimination tendency rather than substitution tendency. So by whenever I say alcoholic KOH, what do I mean by this? I am putting KOH in alcohol, and you need to have greater amount of alcohol in order to drive the reaction forward direction. Okay, because we know that this particular reaction is backward dominant based on strong acid, strong base theory. This is stronger acid and stronger base, and the reaction is predominantly in backward direction. In order to drive any reaction in forward direction, what should I do? I need to increase the concentration of reactants, right? Alcoholic KOH indicates you are having greater concentration of alcohol, which is making the reaction to go in forward direction. If the reaction goes in forward direction, you will be having significant amount of alkoxide, which is a better base than a nucleophile. Hence, it will make elimination reaction to happen, and you will be having an alkene product. If you have less amount of alcohol, you will have greater amount of OH minus only. If you have OH minus, again, the substitution product will be a major product, or you cannot ensure alkene as the major product. My aim is to have, if I'm adding this reagent, my aim is to have greater and greater amount of alkene. If you have OH minus, you have good tendency for substitution as well, not just the elimination. I hope I'm making my point clear.
Yes.
Okay, so in order to avoid the substitution, I'm just picking a nucleophile which is acting predominantly like a base, or I'm picking a negatively charged species which is acting predominantly like a base rather than a nucleophile. Because my aim is to do elimination reaction, not a substitution reaction. Because there is always competition between substitution and elimination. OH minus cannot serve the purpose that because this being a smaller, it also has some good tendency to have substitution reaction, not just the elimination. Hence, I need to take alcoholic KOH. That is, I need to have more and more amount of C2H5O minus. You may ask me why not take only alcohol? Then in that case, you will have C2H5O minus. But C2H5O minus, the alcohol is a weak acid, right? You have very less amount of dissociation. Okay, in order to have greater amount of alkoxide, I am adding KOH to it. Okay, so that the reaction can be driven in forward direction, and then you will be forming some amount of base. Okay, I hope everyone is with me. So what will we do? Whenever in the question paper, whenever you see aqueous KOH, you need to think about substitution reaction. Whenever you see alcoholic KOH, you need to think about elimination reaction. As simple as that.
Got it, sir.
Okay, this is you need to start thinking about those reactions. There are other factors also which may influence. If those other factors are also given in the question, we will be again changing our product. As of now, we are at the starting point. Where to think, how to think. Okay, fine. OH minus is stronger nucleophile than C2H5O minus. C2H5O minus has more basic character, hence it will be attacking the H positive. Amount of alcohol used should be more to make the reaction move in forward direction. If at all the reaction is moved in forward direction, and then only I can have significant alkoxide. Okay, let's go into substitution reactions. So basically we have two types of substitution reactions. One is called as SN1, other is called as SN2. There are some other variations of it, but these are the major substitution mechanisms, SN1 or SN2. That one indicates molecularity, everyone. That one also indicates the order, but it's better to use the term molecularity rather than the order. SN1, whenever if at all they specifically ask what does that one indicate, it indicates the molecularity. Okay. SN2, it is known as bimolecular reaction. Substitution nucleophilic bimolecular is SN2. Substitution nucleophilic unimolecular is SN1. Again, let us take general example. I am taking OH minus, which does the substitution reaction, right? OH minus with alkyl halide, you are forming alcohol. X is replaced by OH, you are forming alcohol, and X minus is the leaving group. If you study the rate of this particular reaction as per kinetics, we will be getting the rate expression as K1 into concentration of Rx. I hope every one of you remember the kinetics part. If I want to write the rate of the reaction, I will be writing the rate in terms of reactants as well as products. If it is a complex reaction, the products also come into picture. If it is some simple reaction, most of the times if you write the rate, it is in general function of only reactants concentration. But it is not necessary, it should be only function of reactants concentration, right? In kinetics, we have seen some questions where you will be eliminating the intermediate and you will be writing the intermediate's concentration in terms of equilibrium constant, because of which you will be having products also appearing. If it's a reversible reaction, in general, products also appear in that rate expression. Agreed?
Yes.
Okay. Fine. You can connect to all those things eventually. Don't worry. So if I want to write the rate of this reaction, this is experimentally determined rate expression. Rate equal to K1 into concentration of Rx plus some K2 into concentration of Rx and OH minus. What does this convey? This conveys that some of the molecules rate is depending only on the concentration of Rx. Some other molecules rate is depending upon concentration of Rx as well as OH minus. Okay. Or if I make K2 as 0, if I make K2 as 0, I can write the rate as rate equal to K1 into concentration of Rx, which says that or which conveys that rate is function of only one reactant, which is alkyl halide, which is not function of the reagent. Okay, this is known as, everyone, some general terms. This is known as substrate. On the substrate, you will be acting or adding a reagent which will be attacking on the substrate to form the final product. Okay, a reagent is the attacking species. A substrate is the one on which attack takes place. A product is the one which is formed due to the attack of reagent on the substrate. Okay, so this is the substrate, this is the reagent. So if I make a K2 as 0, the rate is function of only the substrate, or in this case, the order is equals to 1. If I make K1 as 0, rate will be equal to K2 into concentration of Rx into concentration of OH minus, or the rate is a function of both substrate as well as reagent, or the order is 2. So in general, in the reaction container, there are some molecules which are having rate with respect to first order. There are some molecules which are having rate with respect to second order. So the overall rate is combination of both. In this chapter, we will be seeing conditions when K1 can be considered as 0 or K2 can be considered as 0. We will be looking at conditions when you have predominantly order 1 reaction or predominantly order 2 reaction. But in general, both of them can always happen simultaneously inside the container. We are interested only in the conditions when it is a predominantly order 1 reaction or predominantly order 2 reaction, or it is predominantly SN1 reaction or predominantly SN2 reaction. Okay. Or we will be designing conditions so that either only SN1 can happen or SN2 can happen. Everyone with me?
Yes.
Yes, sir.
Okay, we need to look at conditions or we need to design conditions so that we won't be confused. Okay, we will be having some molecules, or we won't be having some molecules having SN1, some molecules having SN2. We will be having, we can confidently say, yes, majority of the molecules are going to have SN1 reaction. Majority of the molecules are going to have SN2 reaction. So we need to analyze that. Understood? Whenever you have, suppose they don't mention any suppose they are giving some general question where you have both SN1 and SN2 happening. So they will ask what is the percentage of the product which is obtained by SN1. What will you do? Percentage of the product which is obtained by SN1 mechanism. How can you do the calculation?
It will be directly proportional to the rate of consumption of Rx.
Or it will be proportional to rate constant. Okay, so K1 upon K1 plus K2 into 100 will be percentage of the product due to order 1. K2 upon K1 plus K2 into 100 will be percentage of the product due to second order reaction or SN2 reaction. We will look into those questions later on. As of now, we will focus entirely on SN1 or SN2. Everyone
Sir,
with
is
me?
this like a parallel reaction? Like two reactions are going on?
Yes, sir. 2 reactions will be going on simultaneously. Okay. Everyone, shall we start with SN1 and SN2?
Yes, sir.
Everyone with me?
Yes.
Okay. Before that, let us analyze the structure of alkyl halide. Everyone, our intention is to understand the conditions where I can make a K2 as 0. That is, you will be having predominantly SN1 reaction. What is meant by SN1? You are having substitution or a nucleophilic substitution which is following a unimolecular mechanism. SN2 is nucleophilic substitution which is following a bimolecular mechanism. We will see the mechanisms, you will understand. Okay. Let us analyze the structure of alkyl halide. You can have 1 degree alkyl halide, 2 degree, 3 degree alkyl halide. What is meant by 1 degree alkyl halide? Or in this case, initially I have taken a methyl alkyl halide, or the substrate is CS3X. Or you can have a 1 degree alkyl halide, or you can have a 2 degree alkyl halide, or you can have a 3 degree alkyl halide. Okay, let's also analyze the strength of the bond. What is the purpose of analyzing the strength of the bond? And what bond am I referring to? C bond X. Because in all the reactions, I need to break the C bond X. I need to understand the strength of the bond because I have to break that C bond X in any of the reactions. It can be SN1, it can be SN2. No matter what the reaction is, if it's a substitution reaction, I have to break that C bond X. So I should be able to analyze the strength of the C bond X. You may have a methyl C bond X or a 1 degree or a 2 degree or 3 degree. A 1 degree a methyl C bond X is the strongest. What's the reason for that? In all of these cases, you are having a partial negative and partial positive charge on the carbon. We also understood in periodic properties that whenever you have partial charges, there will be generation of extra attractive forces between the atoms because of the generation of these charges. Whenever there are extra attractive forces because of these charges, can I say the bond strength got increased? Agreed.
Yes.
Okay, so a methyl C bond X is stronger when compared to a 1 degree C bond X when compared to 2 degree C bond X when compared to 3 degree C bond X, or the strength of CX bond. The strength of CX bond is methyl greater than 1 degree greater than 2 degree greater than 3 degree. We also understood something similar in case of comparison of stability of different alkanes, right? Strength of 1 degree C bond H is greater than 3 degree C bond H. Hence, as the number of branches increase, the stability is going to increase. We discussed something similar, right? So here also we are doing the same thing. We are analyzing the strength of C bond X. Here I am not breaking it as free radical, or I am analyzing initially before breaking only based on the charges. Because of the charges on the carbon and halogen, there are some extra attractive forces. If you are having this if this partial positive charge is decreased, the attractive forces is going to decrease. In 1 degree, you have one alkyl group, this part donating electrons. In 2 degree, you have two alkyl groups donating electrons. 3 degree, three alkyl groups. So the partial positive charge is going to be decreased in 3 degree to a greater extent. So the attractive force is also decreased to a greater extent. Okay. So CS3X and 1 degree are in general are having a stronger C bond X. 3 degree has the weakest C bond X. So in order to break a CS3X and 1 degree, you will be requiring a stronger nucleophile. The bond being stronger, if and only if I have a stronger nucleophile, I won't be able to replace this X. And what are stronger nucleophiles? Negatively charged nucleophiles are considered as strong. So in order to bring about a substitution reaction in methyl and 1 degree, in general, I have to use a stronger nucleophile or a negatively charged nucleophile. If it is 3 degree, even the solvent can bring about the substitution reaction. In that case, it will be called as solvolysis, breaking with the help of solvent only. A 3 degree C bond X can be broken with the help of solvent only. Okay. Why am I calling it as or why solvent is sufficient? Why am I saying that? Because the solvent is in general neutral, right? If you take water, it will be having some lone pair of electrons, so it can act as nucleophile. If you take alcohol, in that case also it has some lone pair of electrons, it can act as nucleophile. So the solvent itself can go and attack here. If it is a 3 degrees, the solvent itself can go and attack. In that case, it is known as solvolysis or solvolysis. If it is 2 degree, both can do the can serve the purpose. If it is negatively charged, obviously it can go and break because that being a stronger. If it is neutral also, it can sometimes go and break. It depends. Okay. So both can affect the substitution. It depends what you want to choose. But if it is a 3 degree, solvent itself is sufficient. You need not have negative. If it is 1 degree and methyl, you should definitely have negative. If it is 2 degree, it's your wish. You can take negative, you can take neutral, whatever you want. Is that clear?
Yes.
Okay. So if the solvent acts like a nucleophile in the substitution reaction, it is known as solvolysis. Fine. So let's start with SN2. We will understand most of the aspects of SN2 today, and we will start with SN1 probably tomorrow during offline lecture. Once we are done with SN2, SN1, done, we can go to elimination. That is this week's syllabus. Okay. Okay, everyone. SN2, substitution nucleophilic bimolecular. So what happens in SN2 is there is no formation of carbocation in case of SN2. If there is no formation of carbocation, there is no rearrangement possible. Okay. So if there is no formation of carbocation, that means the nucleophile, whatever we are going to choose, it has to be stronger. Why am I saying it has to be stronger? Once it sees some partial positive charge, it will go and attack on that particular carbon without waiting for the formation of carbocation. It doesn't wait for the formation of carbocation. This being so strong, it will directly go and attack without the formation of carbocation. Am I clear, everyone?
Yes, sir.
Okay. So whenever it is attacking, initially the reason for the attack is because of some partial positive charge on the carbon appearing. That is due to greater electronegativity of the halogen. You have partial positive, partial negative. So the OH minus is trying to approach this particular electron deficient site. Whenever it is approaching, that carbon halogen bond is going to break. But before that, we need to understand what is the possible orientation for the nucleophile to approach. Suppose it is approaching on the same side where the halogen bond is there, everyone. It is approaching on the same side where the halogen bond is there. You may not have easiness of approach. Reason being, the halogen, whenever it is leaving out, it will be leaving as a negatively charged species. The nucleophile is also negatively charged. Between negative and negative, there will be repulsive forces. So due to those repulsive forces, this nucleophile may not approach on the same side as the side of the halogen or as the side of the leaving group. So this side is known as front side attack. You cannot have a front side attack happening in an SN2 reaction. Reason being, because of the repulsive forces between outgoing leaving group and the incoming nucleophile. Everyone with me?
Yes.
Yes, sir.
Okay. And whenever, and also one more thing, it has to approach in the same plane. Reason being, this is the bond you are trying to break, right? Okay. This is sp3 hybridized. Everyone, this is sp3 hybridized, which is tetrahedral. If you are breaking the bond which is present in this particular plane, you need to again make the bond in the same plane in order to have the tetrahedral geometry. Agreed? These two bonds, if you observe, these two bonds are in plane. This bond is going into the plane. This bond is coming out of the plane. If I am breaking the bond which is part of this plane, I need to again form a new bond which is again part of this plane. Agreed?
Yes, sir.
Okay. You are having attack on the opposite side. Try to visualize this. Tomorrow I will try to bring those models and I will try to explain. Try to visualize this. Initially, let us say this is tetrahedral. So these two bonds, one is going into the plane, one is coming out of the plane, but both of them are oriented in this direction. So whenever this is coming and attacking, what should happen? These bonds which are oriented in this direction, they will be going to in this direction, but whatever bond is away from you, it is going to remain away from us, but the only difference is it is going to be oriented in this direction now. I'll show you it. Everyone, first understand that this OH minus has to have a backside attack. Front side attack is not possible because of the repulsive forces between outgoing leaving group and the incoming nucleophile. Whenever you are having the backside attack, what is going to happen is there will be a time when this group, and this group, which is CS2D, hydrogen, and CS3, are going to be arranged like a trigonal planar geometry. Okay, trigonal planar, or you can visualize these three bonds as some spokes of wheel. Okay, visualize these three bonds as spokes of a wheel, which are going to be planar. All the spokes of a wheel are in the same plane, right? So these three bonds will be in the same plane. Okay, and you will be having a half bond formation between carbon and OH and half bond breaking between carbon and Br. Only those molecules or only those OH minus can form complete bond which are able to cross that activation energy barrier. Whenever it is attacking, there will be activation energy barrier. You should be able to form more than half of the bond between OH and C. Then only the complete bond breaking can happen between C and Br. If it is forming less of bond between carbon and OH, once there is collision, again this OH minus will be going back and there will be formation of the bond between C and Br. Okay, so only those molecules which are able to cross that activation energy barrier will be able to form complete bond between carbon and nucleophile. Then the carbon and leaving group bond is going to completely break. Okay, so this is the transition state where you will be having half bond formation and half bond breaking. So once this crosses this transition state, there will be complete bond formation between carbon and OH, complete bond breaking between carbon and Br. So these two bonds which are initially oriented this direction, now they are going in this direction because this tetrahedral geometry will remain the same. You need to have tetrahedral. So if this bond is here, these two bonds will be oriented in this direction. Everyone with me?
Yes, sir.
Yes.
Okay. Those who are unable to understand that aspect, I will explain you tomorrow in the class using the pens and all. Don't worry. Okay. So observe one thing. Intentionally, I have taken this carbon as chiral. Okay. If I want to mark the orientation or the configuration, this is 1, this is 2, this is 3. The lowest priority is viewed away from us. So if you go from 1 to 2 to 3, I'm going in anti-clockwise direction. If I go in anti-clockwise direction, it has to be S because the lowest priority is already away from us. So the configuration is S. Once there is an attack, again try to assign the configuration. This is 1, this is 2, this is 3. I'm rotating in clockwise sense, so it has to be R. So what is happening during an ascent to attack or during this mechanism, you are having inversion of the configuration. Initial configuration was S, the later configuration has become R. Okay. And R and S are known as which configurations? They are known as absolute configurations, right?
Yes, sir.
Yes.
Okay. And D and L are known as relative configurations. That is, suppose if I want to know if this is D, let us say this is D, dextrorotatory. What can you comment on the product formed? Anyone?
It can be linked rotation.
If this is dextro, what can you comment on the product formed, the rotation of the product? Dextro or levo?
So we cannot comment, right?
We cannot comment. That's right. Why?
Because they're not the mirror images, and otherwise we cannot determine anything about Dexter and Levo.
Very good. Because they are not mirror images. Unless and until they are not mirror images, I cannot comment anything. Dextro and levo are always experimentally obtained. We need to put the compound in the polarimeter and then I need to see the rotation of the plane polarized light. If it is rotated in clockwise sense, dextro, anti-clockwise sense, levo. So if the reactant is dextro-rotatory, it is not necessary that the product has to be levo because you have changed the group itself. So I cannot comment anything about the rotation, but I can always comment on the absolute configuration R and S. If this is S, most of the times it is going to be R only, unless and until upon attachment of this, the priorities has changed. We have very rare chances of those priorities getting changed. And for all JE purposes, we will simply take, we need to understand the examiner's point of view. If this is S, this is going to be R. I can always make a question which is going to make it as, if this is S, this can also remain as S provided the priorities has changed after the attack. Okay, but don't go into those complexities. In general, we will say that there is inversion of configuration happening, and that inversion of configuration is known as Walden inversion. Walden is the name of the scientist. Whenever the carbon is chiral, there will be inversion of the configuration happening, and that inversion is known as Walden inversion. But if the product, if the reactant is dextrorotatory, the product need not be levo. It can be dextro, it can be levo. Anything can be. It can be anything. Okay. As it is experimentally determined. Everyone with me?
Yes.
Yes,
Yes, sir. So once again, what is the reason in order to have an SN2 reaction? The reason is one of the more dominating reason is the nucleophile itself. Whenever you have a strong nucleophile, the substrate, it won't wait for the substrate to completely ionize. Once it sees some partial amount of positive charge, it will go and attack without breaking off this C bond X. So in order to have an SN2 attack, the first thing to keep in mind is you need to have a strong nucleophile. Okay, we will understand the other conditions later. But the first condition has to be you need to have a strong nucleophile, which will not wait for the formation of the carbocation. as soon as it sees some partial positive charge, it will go and attack. And whenever it is attacking, it cannot have front side attack because of the repulsive force between the leaving group and the incoming nucleophile. There will be repulsive force because it has to approach in the same plane as that of the leaving group, because I need to form the bond in the same plane. As I'm breaking this bond, I need to break a bond in that plane only. Okay, so I'm making a bond in the opposite direction, and whenever you are having that, you are having a inversion of configuration. So if you see the steps, it is a single step reaction. Agreed. This OH minus and this is attacking. You have one transition state and you are immediately forming the product. So it's a single step reaction. For all single step reactions or elementary reactions, the molecularity will become the order also, right?
Yes.
So you have OH minus and this. You have two molecules colliding in the rate determining step. There is only one step, so that step itself becomes the rate determining step. RDS, rate determining step. Okay. So in the rate determining step, you are having two reactants. Hence, it is called as a bimolecular reaction. If I want to mark the rate of the reaction, it will be directly proportional to concentration of this and concentration of this. Raise it to powers only one because it's an elementary reaction. You have only one molecule. So it's a single step. Rate can be written as K into concentration of Rx and OH minus. So the order is 2, molecularity is also 2. And SN2 proceeds with the inversion of configuration. Everyone, let us say the carbon is not chiral. If the carbon is not chiral, then what we are going to comment is that there will be stereochemical inversion of bonds. Whatever bonds which are oriented in one direction, after the reaction, they will be oriented in a different direction. So there will be inversion of bonds happening. Okay. But that particular inversion is called as Walden inversion if and only if the carbon is chiral. If the carbon is not chiral, we will say there is inversion of bonds. If the carbon is chiral, we will say there is Walden inversion or inversion of configuration. Okay. So it is accompanied by complete stereochemical inversion of bonds. If the carbon is chiral, it is called as Walden inversion. Everyone with me?
Yes.
Yes, sir.
Yes. Next. If the substrate is dextrorotatory, it is not necessary that the product has to be levorotatory. It can be anything because it is always experimentally obtained. And in H2O, the rate of reaction, everyone, we already saw the order of nucleophilic strength. In polar protic solvent, for the ions belonging to same group, you need to consider the solvation effects. Whichever is solvated to the greatest extent, its size got increased. Once it has become bulky, it may not approach easily. Hence, the nucleophilic strength decreases or the order of reactivity also decreases. Okay. So in H2O, the order of reactivity is I minus greater than, because after solvation, F minus is the bulkiest. Okay. Hence, I minus greater than Br minus F minus, sorry, Cl minus F minus. In DMSO, the negatively charged is not solvated. So you need not worry about it. So you compare the basic strength, that will become the nucleophilic strength. The order of basic strength is F minus is higher. So F minus is greater than Cl minus, Br minus, I minus. Everyone with me?
Yes.
Yes.
Okay. Nature of substrate, methyl greater than 1 degree, greater than 2 degree, greater than 3 degree. This is written based on steric hindrance. Okay, not written based on the strength of the bond. Because if you observe strength of the bond, 3 degrees C bond X is weakest. Okay. Anyways, we are taking a negatively charged nucleophile, no? As negatively charged nucleophile is taken, you need not worry about the strength of the bond. It can break it. Agreed. Just like in case of free radical reaction, F minus is very strong or F free radical is very strong. You need not worry about reactivity. Okay, or you need not worry about selectivity. No matter what comes in its way, it is going to break it. Agreed. As negatively charged species taken, you need not worry about strength of the bond. The rate of the reaction based on nature of the substrate is commented based on the steric hindrance. A methyl has least steric hindrance. Okay, because you are going to have some crowding effect If you are surrounding this carbon with bulkier groups, it will become difficult for the nucleophile to go and approach this carbon. Lesser number of bulkier groups, easier is the approach or faster is the reaction. Agreed? Hence, the rate of reactivity is CS3x greater than 1 degree greater than 2 degree greater than 3 degree. And for all problem solving purposes, remember this. Okay, remember this forever. For all problem solving purposes, we will never make a 3 degree to undergo an SN2 reaction. Okay, because a 3 degree is going to have severe crowding effect. The nucleophile will have very tough time in approaching that particular carbon. Okay, or it won't be approaching it. Or a 3 degree will never undergo a substitution reaction SN2. Everyone, SN2. If you have a 3 degree substrate, if they are giving you some conditions which is SN2 favored, and they will also give the option which is an SN2 product, you will not fall for it. Okay, you will say it won't be an SN2 product. If it's not an SN2 product, what other product can happen? We will eventually explore. What else can happen? If it is not a substitution, what is the other competitor?
Elimination.
Elimination. Exactly. So you will be doing an elimination and you will be forming an alkene. That's it. Everyone with me?
Yes.
Okay. For rate of reactivity, if at all they ask, we will be mentioning this. Methyl greater than 1 degree, 2 degree, 3 degree. For all problem solving purposes, we will never have a 3 degree undergoing an SN2 reaction. That's it. Take home message. Okay. If you mark the energy versus progress of reaction, initially these are the energies of reactant as well as nucleophile. And always, whenever you perform an SN2 reaction, it is going to be an exothermic reaction. Reason being, observe, a nucleophile is negatively charged. Whenever X is removed, X minus is also negatively charged. So you can always have tendency for a backward reaction. That is, X minus can attack back and the nucleophile has to go out. Okay. Or if you have a stronger bond between R and nucleophile, in that case, X minus will be having difficulty in substituting this because you will be having a greater activation energy barrier for X minus. Agreed? For Nu minus, the activation energy barrier is lower. For X minus to do a reverse reaction, it will be having greater activation energy barrier. So we will always choose that nucleophile which is able to replace this X. That is, which is able to form a stronger bond with carbon when compared to the initial bond with X. Everyone with me?
Yes.
Okay. So you need to form a stronger bond. We will analyze such things later, which is able to replace what. As of now, if you are having a substitution reaction, it is expected that the nucleophile is forming a stronger bond with this. Hence, X is able to be removed by the nucleophile. Okay. The backward reaction is not getting favored because of the stronger or larger activation energy barrier. In the transition state, you will be having half of the bond formation between nucleophile and half of the bond breaking between R and X. Initially, we are plotting the energy levels of Rx and Nu. But during collision, they are able to overcome that activation energy barrier. Those molecules which are having higher energy than this will be crossing this and will be falling in this region. Okay, or will be crossing this transition state and it will be falling in this region. Those who don't have that sufficient energy, they will again form back Rx and Nu minus. Is that clear?
Yes.
Okay, if you have any doubts, you ask me. These are the important points with respect to SN2. Shall we complete SN1 as well?
No, sir.
Yes or no? No, you told me no.
Yes, sir. Because we have to revise this, no, sir.
Okay, fair enough.
Can you do it tomorrow, sir? I want to look traveling again.
Yeah, fine. Everyone,
Thank you, sir.
Could you upload these notes?
I will send it. I will send it right away. I will share the entire notes. In fact, I will be sharing the entire notes. But you also try to take the notes, because for you people, I am adding some extra points, extra problems, as well as extra things. So you, apart from these notes, you also make your own notes. In the classroom, I may share like new points or extra things.
Yes.
Okay, everyone. Okay, everyone, that's it for today. We will meet in class tomorrow. Please go through all the important, minute aspects of it. It's easy. Just understand the essence of it. We will be solving a lot of questions. Eventually, everything will seem easy. Don't worry.